Okay. So hi everyone. So we are very happy to have Atakan speaking today on the use of string theory for D-instantons. So please go Atakan. You have 1 hour and a half, and you can manage the time as you want.
Right.
So please.
Okay, let me share the screen. You can see it, right? Okay. Let me adjust my screen as well. So yeah, today I'm going to talk about this work we did with this gentleman's Sergei Alexandrov, Manky Kim, Ashok, and Bogdan Stefansky. So today I'm going to talk about how we use string field theory techniques to fix the normalization of superpotential in certain string theory compactifications. Okay, so it's based on this paper that we put like last month. So here's my outline. So first I'm going to do a basic introduction, and then I will talk about the worldsheet basics for the setup we use, and the D-instantons for our conventions for the instanton. Then I'm going to talk about how we use string field theory and how we use start with an expression that makes sense from worldsheet perspective, and then make sense of that expression when that the worldsheet doesn't make sense, and then how string field theory solve that the ambiguity. And then I'm going to talk about how we do use that to compute the superpotential and establish its holomorphy. And then lastly, I will talk about the multi-instanton contributions and why they're absent, at least at the leading order. So during the talk, of course, you can ask. So it's a 1.5 hour talk, and I think I have sufficient material. Okay. So let me start with some motivation. So first of all, string theory is supposed to explain the real world. We need to extract massive quarks and cosmological constant hierarchies, all that, starting from the first principles. That's the goal. And then the one controlled way to do it is that we demand n=1 supersymmetry in D=4. So there's a multiple ways to do it, but here's a way to do it based on type 2 theories. Say that we take type 2 theory and then compactify on this 6-dimensional manifold and take Calabi-Yau for that. And it is well known this gives n=2 SUSY in D=4. But again, I want n=1 SUSY because first of all there is chiral fermions in there, and then the way to achieve this is that we orientifold this internal Calabi-Yau. That is, we take the gauge worldsheet parity, we gauge the worldsheet parity possibly with some discrete symmetries, and then consider type 2 theory either A or B on this space. So the question that we can ask is that first of all, how does the low energy physics in 4 dimensions look like? Like we can find a spectrum with the usual using Laplacian, and we should be able to compute interactions. So this interaction is also we want to compute scalar potential. But let's start today. I'm going to focus on the superpotential. So superpotential consists of 2 parts. That is, there's a perturbative part, and there's going to be non-perturbative corrections. So the one of the important effects of the non-perturbative part of the superpotential is from the instantons, which I mean by I take the Euclidean D-branes and wrap into the internal cycle. So they are like we are applying the Dirichlet conditions for all of the coordinates, including time. So which I will call them to the instantons. And then their effect will induce interaction for the fields. For example, it will introduce a mass term for Kähler moduli, and their superpartners. So the expectation for this type of contribution, like let's take a single D-instanton, and it's wrapping some cycles gamma. Which might be like a 2-dimensional, 4-dimensional whole. Anyway, so let's take it, and the from SUSY and the general grants, this is the form that we expect. So we will expect exponential because it's breaking some axionic symmetry, and then with the D-instanton action, and there will be some normalization, and these will depend on the wave of the moduli that we specify. So here I'm not distinguishing Kähler or complex moduli yet. I'm just saying, okay, these are possibly depending on these moduli. But for example, in type 2b, this only depends on the Kähler moduli. Anyway, so so in principle, this superpotential can be computed using D-instanton amplitudes. Which I mean by that is that I take I compute the open string scattering in the presence of the instanton. So of course, I need to draw some worldsheet diagrams. This is the first thing that I can draw. But here's one important difference between the usual string amplitudes, perturbative string amplitudes, is that we can have this type of disconnected diagrams. And because if you have a single D-instanton, it breaks the translational symmetry. So, and the momentum conservation will come after you integrate over the whole possible configuration of that. So disconnected worldsheets are allowed. Another important effect is going to be the bubble diagrams in front. Since we are going to add these amplitudes to the perturbative string amplitudes, this overall normalization will make a difference in this case. So we need to compute this. So the exponential, actually, this is absent. Here, there's two important diagrams. First of all, there's going to be disk, and this disk is, from usual arguments by we heard a few weeks ago that this can be related to the tension. So this is going to be give this part of the superpotential eventually, but there will be additional, and this is proportional to 1 over G string, this is the tension, and there will be this additional part that is just a number, and it's coming from the analyst diagram. So naively, this contribution might look like, I can just write some trace and compute it. But as we will see in the situation we are considering, this is actually IR divergent. So, and the expression we wrote based on worldsheet just doesn't make sense. So, in order, we need to make it some procedure to make this unambiguous, and we will use string field theory and motivate why this string field theory method makes it unambiguous. I mean, eventually it will come to the computing, determinant around caffeine over the square of determinant around the instanton background. But yeah, this is usual bubble diagram logic, which is physical in this case. And then I can compute some string amplitudes. In general, these are depending on G string, and then I can compute them in principle and read off the superpotential.
Atakan, is that expression with bubbles and everything supposed to be the whole superpotential?
No, so the way we are doing is that we are looking for the particular term induced by the superpotential. So the strategy is that, okay, I will consider this amplitude and I will write, so this will give some effective, some term in the effective action. Then based on this expectation we will have, we are going to the read of the normalization based on this particular effective interaction. So is this
but you have a product of an exponential times a bracket. Is that bracket supposed to be A and the exponential this T factor or not?
Let's see. So in principle, let's see. I will say that
so you have this expression with all these diagrams, and you don't say what it's equal to or what is it supposed to be like.
Yeah, so it's supposed to be if I consider say n Kähler moduli and say that I compute their scattering in the presence of the instanton. That's what I'm computing. And then in principle, I need to add this the exponential of the bubble diagram in front because I'm going to add this to the perturbative string amplitudes, right? So this will give me some determine the effective action. And that effective action should be thought of coming from a superpotential, because after all, this is n equals 1, d equals 4 subgraph. So that, this should be generated by some sort of a superpotential. Okay. But I'm not sure, like, so there might be contribution to the here, but I think at the leading order, this is the only thing that is really important. But maybe Ashok can clarify.
Yeah, I think there are probably additional normalizations which come from the disks, but roughly this exponential part is this, the normalization. But I think there will be additional factors of pies and string couplings, etc., coming from the disks as well, right?
Yeah, exactly. So in principle, yeah, I think it's a leading order statement that the normalization depends on the bubbles, but like if you go higher, probably like the amplitudes themselves also make a difference.
Yeah, so ultimately one should just compare the S matrix from string theory to S matrix from the effective field theory. And then read out what the superpotential is.
Okay.
I had a question. Can you remind me, in the superpotential, you said that there's a like perturbative part and non-perturbative part. Is the distinction unambiguous? That was my first question. And what distinguishes them is my second question.
So I'm sorry, what is your second question?
What distinguishes them, like axion shift symmetry charge or things like that?
So here the decomposition that I do is that I think that this is unambiguous. Here's the reason, because I can consider a situation where I don't have any D-instanton, right? And then I should compute this perturbative part. Say it's like there's some flux or something. That's the one scenario.
But what I'm worried about is that, typically non-perturbative contributions are well defined only when you have a good way to say like resum the perturbative series, or perturbative series itself like terminates at some finite order. Mm-hmm. So I was talking about that distinction, because like, for example, in type 2B super string in flat spacetime, like single D-instanton contribution is distinguished because it carries a definite charge, which is not carried by any of the perturbative contributions.
Yes.
So yeah, I'm just not familiar with the generic structure of these perturbative and non-perturbative structures in superpotential. So that's the reason why I'm asking.
So yeah, what you said is correct for amplitudes, but at the level of superpotential, they are different, right? Like the most obvious example is that, say, you take a super QCD or something like that, then you can easily distinguish what is coming from the non-perturbative versus perturbative part, and there are no mixing between that. So at the level of amplitudes, that's correct, because you're adding some additional series to some asymptotic series. So in general, these might be the way you do it can be the ambiguous, but at the level of superpotential, it isn't.
Oh, sorry. Maybe I'm missing your point. So you're saying that superpotential is special in that the distinction is obvious, or?
What I'm saying is that it doesn't have the problems that we have in the amplitudes, right? Because after all, this is just we are just considering some effective superpotential that is generated by it, and like the most obvious way to see it is that, again, I can consider a situation where I have a D-instanton versus I don't have any D-instanton, and then I can just separate those contributions. They are not talking with each other.
Okay, I see. Thank you.
Right.
Maybe I can just add a comment. I think
sure.
Minja said about the type 2B in 10 dimension. I think it's the same reason here, because there it was the Ramon charge, right, which was distinguishing them.
Right.
Here also these carry Ramon charge, right? So for example,
see.
now translation invariance is broken, which will be not broken in the perturbative superpotential.
I see. So is it possible to distinguish this perturbative part from, say, DD bar contribution, for example?
So DD bar doesn't carry any Ramon charge, right? So that actually is, yeah. I don't think that can be distinguished by this directly.
I see.
Yeah. Ashok, you're saying that this basically this exponential is that what's distinguishing them, right? Like
because this depends on the Ramon field, right? Without derivatives. I mean, it's just it breaks the shift symmetry, Ramon shift symmetry, right? which perturbative part doesn't do.
Thank you.
Good. Any other questions? Okay, I will carry on. So this was just some formal expression, the way we are going to do it. Like, so I'm going to compute some amplitudes with the correct fixing the correct normalization, and then read off the superpotential from that at the leading order. And then the way we are going to do it is that the comparing with the n equals 1, d equals 4 supergravity, which is what I said here. And along the way, I will show that this fact that the superpotential we obtain is holomorphic, which should be the case. And then then I will say that some words about the multi-instanton contributions if I have time. Okay, so let me start with some worldsheet basics for this situation. So we are taking type 2B theory because it's easier to deal with because the identical GSO. And then this will consist of the 3 parts. So we are going to have the usual part that is describing non-compact directions, which is x mu and psi mu. And I have a ghost part, and I will add I will consider Calabi as some 2,2 superconformal field theory instead of some the nonlinear signal model with Calabi target, because this will give n equals 1, and our arguments will be actually independent of whether I have a geometric interpretation for the internal manifold. We will see the advantage of in certain cases why this point of view is better. So okay, they add to the central charge 0. And then
sorry, just to clarify, so you are assuming that you're dealing with pure NS flux?
Yeah, no fluxes in this talk.
Okay, thanks.
Yeah, the fluxes is this complicated, right? No.
Yeah, thanks.
So, okay, so this as I said, this will give n equals 2 Suzy and d equals 4. Next, I'm going to do oriented folding. Which we define by this. That is, I'm going to project out to the +1 sector of this operation, and this will eliminate 2 of the super currents, and then this will give n equals 1. So I'm sorry, 4 of the super currents, and it will give n equals 1 to the n equals 4. So, and then another thing that you have to describe is the D-instantons themselves. So, as I already mentioned at the beginning, I'm going to apply Dirichlet boundary condition for the non-compact direction, which is x mu and psi mu, and then Neumann for the ghost. And there will be some boundary condition for the internal CFD, which I'm not going to go into the detail, but we choose it in a way that there is this additional charge for this equals to superconformal field theory, and this we preserve this U1 charge if with their boundary conditions. Anyway, so it is important to count the 0 modes, because after all, these are going to be the ones that are going to cause the IR divergences. So we are going to consider a single D-instanton wrapping a cycle. Also, I will assume its image is itself under the oriented folding. These are called O1 instantons. They are particularly simple. So let's count the universal 0 mode first, which I mean that the L0 vanishes, of course. So before oriented folding, I will have 4 translational modes, right? I can put the instanton anywhere I want, and it shouldn't. There shouldn't be any kinetic term associated with it. Like there's no energy associated with moving around. There's 4 Goldsteinos because it will break the half of the SUSY, which is n equals 2 in this case. And there will be 2 ghost modes that are basically coming from the gauge symmetry on this D-instanton, rigid gauge symmetry. But after oriented folding, one can show that the only subset of this 0 modes is going to survive. The 4 translational modes is going to survive, and there is going to be 2 Goldsteinos are going to survive. This makes sense, right? Because we break the n equals 2 SUSY in d equals 4 to n equals 1. In d equals 4 now instanton should break the half of that symmetry. So and you can see from worldsheet that is indeed the case. And for, like, these were the universal zero modes, and we will assume no other zero modes are present. For example, it may be possible that I can move this instanton inside the color BL, but for this talk and for simplicity, we are going to assume that this is not case. This is not the case. It's just a rigid instanton. Okay. So, are there any questions before I move on to the normalization part? Okay. So again, like we want to compute the analysis partition function with the effect of orientifold projection. So here, introduction, I just wrote this, but since we know now there is a orientifolding, we need the Mobius strip contribution as well, which I denote by this, where I identified the two other boundaries. And first thing, if you see this expression, the first thing that you will write from worldsheet perspective will be this. That is, you do some modular integration and you consider the ZA and ZM, which are defined by the trace with the, trace over NS and R sectors. So there are like a certain parse, like this expression is the usual one. I'm taking a trace over. And the minus F is that describing the space-time statistics. And there's some various factors of 1/2. That is first over 1/2 coming from the orientifold projection itself, right? Because it's 1/2 this. And the omega is that is going to the Mobius strip. And there's additional 1/2 to the R sector because they are fermions. Okay, so this is what we will write. And then you look at this, okay, if this integral makes sense. So in t equals 0, we are safe because there's no closed string tachyons in this situation. And there we are going to assume all tadpoles are canceled in this situation. And then this integral should make sense. Yeah. Like it makes sense as a sum though. And if you try to separate them like this plus the 0 to infinity, we will see that in general, those two things can be divergent at t equals close to 0, but there's going to be some organization that I'm going to do soon that we can separate those two terms. So the real problem is that the t goes to infinity limit. That is because, as I claimed, there's some zero modes. The L0 is going to vanish. So, and if I take the t goes to infinity, this term is going to give some divergences. And then and that's why this expression that we wrote for the worldsheet just doesn't make sense. So, and here's the part that the string filter will come in. It will make sense of this expression, and it will give a right thing to replace it with. Okay. So this is the usual step. We are going to make sense of this formal expression using string filter. So let us start with organizing t goes to 0 ends. So here, the one, what we can start with the separating this integral into two parts, where I put delta into the middle so that I can separate the contribution that is picking up when the cylinder is long, the cylinder is long versus where cylinder is long. There's a closed string propagation versus open string propagation. So since this is about the long cylinder, it is better to go to the closed string channel and then we can interpret the term that I wrote over there as a sum of two terms, which is one coming from terms like this and one coming from this. So by the way, when I say ZA, I'm considering where the ends of the open string either ends in the instanton or like a space filling brains that might be present in this situation. And when I say ZM, one is at the instanton and the other is at some O plane. Again, since this is some orientifolding, we need to add those stuff to cancel tadpoles. So I can separate into two contribution, which is this one, which is again instanton and instanton the total boundary state of the space filling brains and the Mobius strip, and here are their expression. So this isn't like here I'm converting the closed strings, and that's why I take this boundary state formalism. And the crucial difference here, this is like a usual, modular transformation type of thing that we did. The crucial thing is that the way we do it for the annulus versus Mobius strip is differ by this 1/4. And this is if you remember type 1 tadpole cancellation, it's essentially the same factor that's coming from here. So but there might be possible divergences as the total term is like should be safe when I take L infinity, but since I separated those two contributions, there might be individually divergent, and these divergence should be guaranteed to cancel. And then so we need to do some organization. So there might be some possible divergences coming from the closed string zero modes, massless states, massless closed string states, and this decomposition might not be possible. But it turns out they're absent. Here's why they're absent. First of all, I consider instanton to instanton, which is this diagram right there. And since this is the instanton, its boundary state contains some momentum factors with 1/k² coming from the closed string propagation. And if you now you do this integral, you will see that it's actually finite as k goes to 0, where there's a long propagation. So there's no divergence from here. Second, again, as I emphasized many times, we assume tadpoles are canceling. So the boundary state for D branes plus the all planes does not source any closed string states. It shouldn't. So from this fact, we can write this combination of terms as like manifest the finite form. That is, basically I'm writing what I wrote about for the closed string channel into more manifest the finite form. So this is finite, as I argued at the first point. This is finite because this doesn't source any zero mode term here. So this integral is finite as L goes to infinity, and this is also obviously finite. But from this, the way we do it is that but this is equivalent to putting some uniform limit to the L integration, right? Because here's my term, and here I claim that this is finite because of tadpole cancellation. Another way to say it is that I can separate these two terms and put 1/epsilon for this infinity and separate these terms and take epsilon to goes to 0, and then they will cancel because of my assumption. But and then when you turn this when you turn this argument, this limit to the open string channel back, which is going to something proportional to 1/t. What you have to do is that the way you should separate this expression is as follows. So again, like if you naively separate this ZA and ZM, both might be divergent as t goes to 0. But if you do put this uniform bound, which translates into this bound for the open string channel, they actually still cancel each other. And again, like there's this 1/4 difference because there's this scaling difference between the annulus and the Mobius strip. So both of these expressions in total, this limit will make sense. Okay. And the fact, you might be wondering, okay, why do you separate these integrals? But the reason that we really want to do it is ZM and ZM will be depending on the CFD, and we can compute it. And the expression that I will wrote, that as long as you know those partition functions, you can just put in and compute your overall normalization. So this is very convenient way to organize this contribution that we'll see. Okay, are there any questions about this point? So here I'm just doing some organization. Okay. So now let's focus on the t goes to infinity around the infinity region where the open string states are going to propagate. And this is the part that is really problematic in certain sense. So in order, so there's IR divergence because of zero modes, as I said. So there's the way to in some sense regulate this is put the slightly shifted boundary condition at the bottom. So, and then which is, you know, it means that I'm basically separating, like thinking I have two instantons instead of one, and they are separated in the third space. So this means that like if I do that and if I separate them far enough, this expression that I wrote for the annulus plus Mobius strip, which was trace over some, trace over NS and R sectors, which is also can be written like this form over the spectrum, over the modes rather. We can, if I separate those separate far enough, I can write this expression in terms of this, where the weights are always greater than 0. If there were 0 modes, this one of them, few of them might be 0. So and then then the integration, when I try to do integration, this will make sense as t goes to infinite limit. Here, by the way, this SR and SA tilde are the denoting the Grassmann-Hilty of the modes, because I can have bosonic or fermionic modes as usual. So now my integration makes sense. So now I can play with it, right? There will be no ambiguity with this separation of the boundary, the slightly shifted boundary condition. So let's separate this sum into 2 parts, which I will denote by prime and double prime, and demand the following for the prime set. So prime set, I will basically take all 0 modes into this prime set. When I say 0 modes in this situation, of course, there's no 0 modes in this deformed boundary condition, but when I remove that deformation, there will be modes that will have 0 weight, and I'm going to include those modes into this prime set. I will assume that these are appropriately normalized, which I will comment on more when we write the SFT quadratic term, what I mean by that. And then the demand this prime set satisfies this condition on the Grassmann parities. And then the double prime will be the rest of the modes. And the reason that I demand this is the following, because if I, as I said, I can separate the integration makes sense, so I can separate the modes from each other. And if I perform the integration over the prime set, this condition makes us allowed to evaluate the integration without any delta dependent term, which is an important thing to do, because then I can take this whole expression and write in this following form, right? Basically exponential, like combining the double prime part and exponentiating this and write like this. So the delta information contained in this part, which is finite, and there is a prime set part, which is going to be the ambiguous as I remove the deformation. So the important insight here is that we can interpret this part as the integration over the quadratic term of the gauge fixed open superstring filter and D-instanton. That is, I can write this expression like this. So this is just the identity in the deformed boundary condition, right? And then here's my quadratic terms, phi ns and phi r, right? This is just basically this is a determinant, Pfaffian over square root of determinant, and I'm writing a Gaussian for it. And then since I demand this prime set is appropriately normalized, this will give the correct expression. And here is that the additional 1 over square root of 2 pi that we pick up for the bosonic modes. And before I move on like this, all I did is some organization at this point. I put some deformation, then I organize my terms so that the expression look like what I have in string field theory. So in some sense, this makes sense, right? Because we are computing bubble diagram. And if you consider your PFT, this exponential of this bubble diagram should give you this Pfaffian over square root of determinant, which is just the integration over the quadratic term. And we are doing in a way that the part that will include 0 modes plus additional modes that we put into the prime set. now we can take the instanton to the same place, that is remove the deformation on those boundary conditions, and give meaning our formal expression as like this. That is, I had this t goes to 0 part, I added that back. I have this double prime set that I separated earlier. And then I will interpret this part as a measure coming from string filter. So originally, when I wrote the worksheet, this part didn't make sense, but I can give sense to it now using as since I wrote as the integration over the quadratic term of the string filter action, I can just use it for this in the case of 0 modes too. And there's an extra 1/2 that we have to add because this is a O1, which is a Z2 gate symmetry that is we need to divide by this gate symmetry when we consider gauge on fixing. So, Ashok's old work is there are additional modes that were present and we need to do full gauging on fixing, but here's just a number. Okay, so this expression now makes sense. I interpret this bubble diagram as a integration over the 0 modes. Basically, that's what it is. And these are the things that are coming from massive modes that I haven't give meaning to haven't evaluated because they are finite and make sense. Okay, so let's look at the prime set more deeper. So we have this, and this will contain 0 modes, this is translational for translational modes, and 1/2 2 Goldstinos, and minus because they are fermions, and plus additional massive modes that I have to put because I need to have this identity that I demand to satisfy, which gives me this. So here, these are the way I community defined by the Grassmannian parity for the NS and the 1/2 difference in R. And these should satisfy the -3 because I want them to satisfy this particular identity. So more explicitly, using this evaluation of the prime set, I can write the expression that I wrote earlier as follows. So I have 1/2 again. I have the t goes to 0 part, t goes to infinity part. Now double prime is written in a way that I just interpret as a different, you can interpret double prime as the whole set minus prime, which was this one. And I basically put the 0 modes plus the additional modes. I think and that I related for this additional massive modes. So you can show that this is actually independent of this yi weight that I choose as I remove this deformation, and I can pick them to the same number. And the second line turns out to be manifestly finite. And the easiest way to see it is that as t goes to infinity, this just dies out, right? It's because yi are positive. And there's -3, and this ZA and ZM contains effectively this amount of 0 modes. So it becomes 3 minus 3, which is 0. So it's finite. And so we can conveniently write this, since this is finite, I can basically separate all of these terms by putting a uniform bound, which is 1/epsilon, and separate them. And then you just combine with this integrals to eliminate delta and rewrite whole expression to get this form. So this is our final expression. So again, all I'm doing here is that I'm trying to interpret this formal expression we wrote for the worksheet, put some deformation to match the string filter expression, then say that, okay, the string filter expression should make sense in the case of 0 modes, which giving me this, that is integration over the 0 modes plus the massive contributions. And the massive contributions are defined like this. So to remind you, the Zn and Zm was the following contributions. That is, I have some instanton, the space flowing brain, and for the all planes. It turns out this is actually 0. So it's because of the effective n equals 2 SUSY. So we only need to consider these 2 terms. And further, you can set h to 1 because it's a irrelevant number. And then give meaning to this bubble diagram I had. And then the unit to deal with the zero mode integration. So this was a long procedure, but as I emphasized earlier, this is just a separating zero mode integration in a well-defined way. So before I continue, are there any questions about this? Because this is the crux of the argument, crux of the paper. Why this makes sense? And as I said, like if you know these numbers, if you know this partition function, you can just put in, evaluate the integral with this properly placed limits and just get a number. Okay. So there are a few things that we have to do still. So first of all, we have this psi mu, which was denoting this translational modes, are related to the position of the instanton after a field redefinition. So, and this is the field redefinition that we have to use. So there's some power G zeros. And this can be found by demanding this e to the IP psi tilde dependence, so that when we do the integration over these modes, they will give a momentum conservation delta function. This is you can find it in the Ashok papers how to do this. Then we need to do saturate some zero modes. This is like Yang-Mills instanton. If you basically it's basically we are doing some string version of that, and placing two vertex operator for this Goldstino zero modes in all possible ways to amplitude that you're multiplying this bubble diagrams to. And I will denote this amplitude A alpha beta. Alpha beta is for the Goldstino's index, spinor index. And then the final result that we wrote for the amplitude will be as follows. So again, 1/2, there's this 1/2 coming. I added the disk contribution, the parts that is coming from field redefinition, overall normalization, massive modes, amplitudes, and delta conserved delta function. And this is all making sense now. Okay. So good. So far so good. So let's do as an example that the in particular case of amplitude, say that I want to compute the correction to the mass term for superpartners of Kähler moduli. And then I already know the overall normalization. All I need to do is that to compute this amplitude where I have the chiral fermions that is like superpartners of the Kähler moduli with the insertion of this Goldstino zero modes, and I compute this amplitude. So this is some amplitude computation which you can find details in our paper, and then you can write this in terms of the derivative with respect to the Kähler moduli. And the instanton amplitude in this case becomes this. And there's a generalization you can consider Kähler moduli itself, like not just, you get a bunch of Kähler moduli to the like this and get those amplitudes as well. And then once you have this expression, you can write an effective action that generates this amplitude, right? So yeah. Before I go and do this comparison with the super gravity, are there any questions about this procedure? Because this is the where the string field theory's powers comes in, that just fixing all of these numbers in this way, especially in this case here. Okay, so let me move on to the superpotential and how we compute it. As I said. I can write the effective term and the term in an effective theory whose vertex is basically going to generate the amplitude that I wrote, which is you can do it in this way. So the expression is not really important. The fact that you can do it is important, because again there are subtleties that we compute in a string frame. You need to convert to the Einstein frame, canonical normalization, etc. So it requires some care, but this can be done. So then you say, okay, I know my symmetries in the low energy theory, which is n equals 1. It should be n equals 1 supergravity. And then I look at the Lagrangian and try to find the superpotential which will generate such a term. So there is this coupling, there's this mass term that we have in the Sura. You open your favorite supergravity book to look at this. And then we know that the expected form, required form. And you basically take this in, put in here, and just like compute, keeping the only leading terms, and basically get this expression for the superpotential. So this is very straightforward procedure. Basically, we are reverse engineering amplitudes to the superpotential. And this is the form we get. So first of all, let's do some consistency check. So this is invariant under Kähler transformation as it should be. So there's no issue there. Another check, and it depends on the correct way up to some phase, etc. The important thing is that we need to check is that, okay, Kähler transformation is the one usually what you have to check when you have an expression like this. Another one is that the holomorphic, right? We know the superpotential has to be holomorphic. So that's the natural question. So is this holomorphic? Because there's this term. Let's put plus. There's this Kähler potential term that is non-holomorphic in general, and it's not entirely clear how this K0 and this term are going to interact with each other to cancel the non-holomorphic, make this whole expression holomorphic. So it turns out this expression is holomorphic, but we have to use this Kaplowski-Lois formula for supergravity and use some facts about the representation of this n equals 2, 2, n equals 2 superquantum homology. So first, let me start with the Kaplowski, give a brief overview of what this formula is all about. So this is basically the generalization to the supergravity generalization of the fact that the one loop, the coupling in the coupling of supersymmetric gauge theory is one loop exact. It's again, you see, when there's no gravity, we know it's one loop exact, at least holomorphic gauge coupling. And this is this part. But if you couple to the gravity, make a supergravity theory, you need to add this additional term that is take care of this Weil anomaly and Konishi anomaly. So this is a standard result in supergravity. And then this is the first aspect, this first formula that we have to use. The second is that we need to relate the amplitude, this formula, because this is for the gauge coupling. So we need to relate this to the instanton in some capacity. And the way we do it is that we are going to consider D-instanton as a Young-Mills instanton where we replace the D-instanton with the space-filling brain. So more explicitly, say that I have a E3, the D3 brain wrapping some cycle in Calabi-Yau. So it's wrapping some divisor. And then this has a Dirichlet boundary condition in the non-compact directions. What we do is that we first replace the Dirichlet boundary condition with the Neumann boundary condition. So it becomes, instead of P brain, it becomes P plus 4. So it's like D3, D7. And then consider this instanton configuration as a Young-Mills instanton on this brain. Then we establish the following relations. That is, if I consider this amplitude right there with the instanton, the some space filling brain, we establish that if you turn on some fluxes on this the replaced brain, which we call probe brain, and take derivatives, it produces the right amplitude. So then from these two facts, that one can translate the holomorphy of this gauge coupling to the holomorphy of the superpotential. So before I explain how we did this, I mean, this is like this was a folk theorem in some sense. Like people always write expressions like this, but we give a first principle proof. But before I do that, so let's say this expression is true, and then we connect this way, and you can just rewrite your superpotential in the following way. So it's just that you do some algebra. Details are not really that important, but basically you relate this K0 expression manipulating a certain way to write whole expression as like this. So as you can see, this expression becomes manifestly holomorphic because this was holomorphic and this was holomorphic. And we say that, okay, yeah, that this is indeed a homomorphic function of the moduli. So before I go to the proof, are there any questions about this? What we're trying to establish? Because what we're trying to establish is to take this, the statement about holomorphy in the probe brains and translate into the D-instanton. That's all we are doing here. Okay, let me briefly give a sketch of the proof for these relations. I thought this result wasn't really neat. So the way we have done this is that we consider the instanton amplitude, this cylinder amplitude, and write in terms of free plus ghost partition function plus the internal superconformal field theory representation. Remember, this was n equals 2 theory, and then this was n equals 2 superconformal algebra, and there's an extended superconformal algebra that includes the target spacetime supersymmetry, and their representation has been classified. So there are only like a finite number of them. And basically, we consider representation by representation. That is, we take this expression, and then we do the replacement that I described. That is, I just replace Dirichlet boundary condition and for non-compact direction with the Neumann one, and turn on some fluxes. So this will result in some twisting in the free field part with some addition of momentum, etc. But that, of course, there are many subtleties and many factors of minus and half that we have to deal with. There's inclusion of momentum that has to be done correctly. You have to take into account Landau levels because you're turning some magnetic field. You need to replace the O1 instanton with the SPK. There's this additional sign that changes the orientifold action on this brane. So instead of OK, you get SPK. So you need to take care of this. And there was, again, many more signs and one has to deal with. But after all this dust settles, you establish that there's this common ratio minus 8 pi squared, which was what was the expectation all along. Anyway, the fact that we may be able to do argument like this is that the fact that this representations for this internal superconformal field theory is like very explicit. And of course, we know the free part. Anyway, okay, so let me briefly mention this multi-instanton contributions. So this is basically say, okay, we have done this, the O1 case. Basically, we take this, let's say, put k instantons on the same cycle. This will have an OK or SPK, depending on the situation, and a line on top of each other. So then we do this whole procedure again, fixing normalization. But there will be this additional term that is coming from the off-diagonal modes. Right now, we will, of course, have more zero modes, not just like describing the motion, but describing relative motion. This is the expression that we get. So the details are not really important. The important point here is that there's going to be some unbalanced, undotted, and dotted. Oh, sorry. So it should be dotted. I think it's dotted. So there's an imbalance in the dotted and undotted Fermi zero modes. And then the fact our effective action is always this dotted and undotted modes always comes in pairs. So if you want to get like a non-zero expression, that you need to make sure that these are balanced. And at the leading order, this only happens when you have a single instanton. But in fact, you can say, okay, what about the subleading corrections? I can add this dotted fermions. I'm sorry, this was dotted. Let's see, anyway, so you say, okay, I can add this dotted fermions to the amplitudes and saturate the zero mode integration, get some non-zero term. But it turns out this is the two conservation laws doesn't allow you to do that. That is, we have this, we have to satisfy picture number, make sure the picture numbers work correctly in this situation. And we also need to make sure that the J charge conservation works correctly. But it turns out, even if you use this term for the PCOs that is contained one, you cannot saturate them at the same time. So it turns out this vanishes. So, but of course, there is some loopholes that this we are considering, because if you add one instanton, there is not some runaway behavior. So it's, in some sense, we are ignoring those effects or like considering leading order in those effects. But the argument is saying that, okay, the leading order and the subleading order is vanishing. Okay, so I was a little fast, so so that there will be a lot of time to discuss. So let me conclude and describe the outlook, what we can do. So today I described how one can read off the instanton contribution to superpotential for type 2b on the Calabi-Yau intervals. We seen it was a holomorphic in moduli, and the only single one instanton was contributing. So what are the next things that we can do? So there are a few options that one can build on. So first of all, we only gave a recipe here for this this overall normalization. We haven't evaluated this K0. So this K0 depends on the massive modes, and then in general, our a priori expectation will be this depends on the model that we're talking about. So, for example, one can try to do something like starting with the exactly solvable models, some orbifold, or like some Gärtner model, and then they compute this number because we can classify the representation and they compute this partition functions appropriately, and then perturb the weights around that to see how it changes. That's a work in progress that we are thinking right now to find a suitable model that one can do this. So another interesting direction is that to turn on some fluxes, which is the most simpler one will be NSNS. Because in general, if you turn on NSNS fluxes, some of the zero modes in the multi-instanton contribution should get lifted because there are additional interactions. And then they should balance this number in the multi-instanton case and give some non-zero answer for those. Actually, that seems to be the expectation. Then maybe one can do some dualities to map to the RR flux cases. And then another general comment that I have is that now we have this like non-perturbative data, not this in this situation, but the type 2 situation with or without compactification. We might try to like understand how this resurgence in this case would work for the string perturbation theory, and what can we learn about it. And maybe this will give some nice insight in non-perturbative structure. So this is all I'm going to say today. We can discuss. We have more than enough time to discuss, I guess. So thank you.
Thanks a lot, Atakan, for the talk. That's very entertaining. So do we have any question for Atakan? So as usual, we can have first discussion with recording, and for people who don't want recording, we can stop later and continue to discuss.
Also, when you were computing the normalization, I remember that you were ignoring for the moment the possible like moduli modes, right? The moduli of the, say, intermanifold. And then I got confused when you came back to this issue in your final expression, because like then you were also talking about the holomorphy of the superpotential and so on from there. So I was just wondering if you can like argue that ignoring those moduli modes when you were computing the normalization is all fine and good for the discussion about, say, holomorphy and so on later.
Yeah. So so first of all, this holomorphic modes business is that we need to distinguish two things. Zero modes are like coming from the D-instantons themselves, right? These are the zero modes on the D-instantons. We are considering a string filter on top of this. So okay. So the moduli should enter implicitly to this K0, and then the fact that how we put the instanton, like how the cycle is defined essentially. So these are separate questions, right? Like it's
I see.
Moduli can be massless, but the way we are doing is that we say, okay, I picked this certain web for that moduli, even though there's a flat direction, and I'm just computing around that web. Then there's a superpotential, and it induces some some potential for that web, right? And then
I see. I see. Thanks.
Just to summarize, many of these things were already done about 10 years ago. So the novelty is the exact computation of the normalization.
That's correct.
Because it was more or less guessed at that time, well, because, okay, there are arguments which allows to try to guess the result. And, okay, so this is the main point.
Yeah, like the novelties is basically making sure that these numbers right there are like correct. Again, like this, people usually did this 10 years ago as a, inspiring from the Yang-Mills instanton, right? They say, oh, the Yang-Mills instanton, this is how we do it. We just write the zero modes to integrate out, and don't worry about, like, basically they take those inspiration and just wrote the expression directly without considering the normalization. So, and that gives some insight. Basically all the novelties that we did the numbers correctly here using string field theory.
Okay, just to continue, because the starting point you used, the expansion, the exponential of the disk and so on, is not very field theoretical. It is more or less more close to the usual string theory, where you think of a particle. In this case, you are thinking of D-instanton as particle, and so you are adding diagrams. Is there any chance of having a true background with instantons, which is a solution of everything? Not just adding one instant to instanton as they were particles.
I see. So you want to do is like seeing instanton as some sort of
like you do in a QCD.
Yeah.
You have the instantonic background, and then you consider particles and what happens in this instantonic background. But it is a full solution of a full non-perturbative solution of a field theory. In this, I don't say that you cannot reach the same result, but the question is there any chance to have such a kind of a solution which is by far closer to the spirit of the field theory, and hence to the spirit of the string field theory?
I see. So let me be clear. So you want to say, okay, I want to describe this D-instanton as a true, like, instanton solution of closed string field theory, say. Like,
yes.
Is that? Yeah, that's a great question. Like, it's that should certainly that should be done if it is possible, but it's I don't know if we can do it right now. But in any case, as you said, the results should be expected to be the same, but without sufficient technology in closed string field theory, I don't think that one can do it currently. You need to solve that equation of motion, right?
Okay. Thank you.
Actually, I think in the past, when people described instantons in Yang-Mills using the instanton picture, there actually was a way to do this, right? So, I mean, they didn't phrase it in string field theory language, but I think from like modern perspective, what's happening there is like the following. So you have the usual action, but when you have in addition like the instanton, then you have the instanton induced contributions to your string field action. Typically, when we try to compute the like amplitudes and so on, we would like to integrate out the modes on the D-instanton and get the physical answer for the say super Yang-Mills fields. But actually, I think if you just leave the moduli like D-instanton moduli unintegrated, and still you have the this like action which contains all the modes in the D-instanton and the Yang-Mills, let's say, then if you actually look at literally solve for the linearized say the kinetic term together with the term sourced by the D-instanton, I think that thing exactly gives rise to the usual Yang-Mills D-instanton solution. Instanton solution. So I was actually wondering, I was wondering about this like a few days ago, but I was actually wondering like if you could do a similar thing for the closed string field theory case, where you have the usual say like graviton and I don't know like delta profile in the say like in type to be flat Sugar background. People write down this delta which goes like 1 over r to the 8th, I think, background. That's the expected instanton background. That's actually nothing but the Fourier transform of just like 1 over p squared, which is the just inverted kinetic term. And all one needs is the like source for this term, and that source I think is exactly given by the D-instanton. So I think somehow if you just maybe I'm missing. Sorry.
So let me be clear. So what the old computation is done by this this type of replacement trick that we used here, right? They replace the D-instanton with some fluxes on the bigger brain, and then use that to write the instanton solution. Am I correct?
Oh, I'm talking about even the simpler one. So just in let's consider the simplest setup, which is say like type to be in flat space. Mm-hmm. Then you have a Sugra description, right? Mm-hmm. Yeah. All I'm saying is that in Sugra description, people write down this like instanton type solution, where the say delta profile, for example, has 1 over r to the 8th. Yeah. That's all I'm talking about. And now we are wondering if one can actually recover that from string field theory point of view. A few days ago, I was thinking about this, and I thought that maybe we have the usual kinetic term for this delta profile or delta fields. Of course, equals like 1 over p squared. But then we also have the source term from the D-instanton. It's like 1-point function of delta. So if you simply solve for the equations of motions coming from this action, then that thing actually looks exactly like the the tau profile. So I was wondering if this is how we should actually think about the usual low energy effective field theory instanton solution from the perspective of the string field theory. I don't know, maybe conceptually this is not the right thing to do, but when I just looked at the formula, it looked like that's the way it works. And this was largely motivated by looking into the papers by, I guess, Igor Pesando. Was also part of this story, like where one tries to describe the, say, ADHM solution from the perspective of the instanton in like D-1 system. And when I tried to reinterpret that from modern string field theory perspective, I realized that this is how we can possibly interpret it.
Can I add a comment that it seems that if you really want to think of the D-instantons or any D-branes as solitons and instantons, the natural setup is the open string field theory on the brain anti-brain system, right? You can imagine that you fill the space-time with the brain anti-brain system, space filling, and then the vacuum is the usual closed string vacuum. And there all the lower dimensional D-branes come as solitons, right? And so that I think will be the natural setup for describing the D-instantons as regular classical solutions.
You say it won't work in closed string field theory, or like that?
So you don't, instead of using closed string field theory, you can take open string field theory on the brain anti-brain system.
I see.
Take a pair of space filling brain and anti-brain. So the total charge is 0. And when you condense the tachyon, the ground state just gives you 0 energy. That's a perturbative vacuum. But you can also construct solitons, right? Where you twist the string field. And those are reasonably well understood. I think, okay, instantons, I don't think people have actually constructed, but for example, the codimension 1 soliton certainly can be seen by level transition, right? And I don't think that it's that much different to get this codimension 4 solutions. So there, I think it will be more like a regular instanton, right? Whereas if you try to think of it from the closed string viewpoint, I mean, often the solution is singular. Right? I mean, Green and Gutperl, I mean, they attempted to construct the instanton as a solution in supergravity, right? And they did encounter some singularities. And in fact, the other problem that they had, I think, is that the instanton was complex solution, right? They didn't get it as a real solution of a string field theory.
I mean, that's what I was suggesting earlier. Like, is it possible to like consider this complex solution of the closed string field theory, and then maybe in a way that Min just it's like, and then because I mean, this is supposed to describe some sort of tunneling in closed string field theory, isn't it?
Yeah, this is true. But from the open string field theory viewpoint, it's actually a real solution because this is generalization of the usual Young-Mills instantons.
I see. Yeah, that's much simpler.
So it's much simpler because I mean, even to determine what the integration measure is, right? Whether you are integrating over half the contour or the whole contour. Once you think of it from the open string field theory perspective, because it's a real solution, the contour just goes through it, right? So you know that you have to integrate over the full contour.
Thank you.
So it seems that one can get more insight into these instantons by regarding these solutions in open string field theory rather than in closed string field theory.
Can I add a question to this, to Ashok?
Yeah.
Yeah. So if you take this brain-anti-brain configuration, so there would be the tachyon vacuum probably would be the closed string vacuum, correct?
Yes.
But you would just say that the closed string field theory are perhaps not a good choice of variables to describe these particular excitations. So that's why it looks singular.
That's right. Yeah, exactly.
Yeah. Okay. Thanks.
Yeah.
Mm-hmm. Thanks.
So do we have more questions for Atakan? Okay, so it seems not. So I will stop the recording, and then if people want to ask more questions, we can continue.